Our intraocular lens calculations are based on keratometry readings, and it's important to recognize that it's not that the lens calculations are based on any sense of what kind of the true cornea is. They're based on keratometry readings. And we want to produce a value after LASIK surgery that's going to be able to really mimic keratometry readings. Well, the most obvious question is, why don't we just use the keratometer? And I'm sure that you know what the answer is, but humor me, let me explain it anyway. This is a computerized topography of a normal cornea. And there are several things that we notice. One of them is that the different powers that are given by the different color zones here are all pretty uniform. The powers don't change much for the central cornea. For the paracentral cornea, you really have to get out towards the periphery, towards the limbus, to start getting into different curvatures. The other thing that you'll notice in this picture is this black and white dashed circle that surrounds sort of the center of this map. And this is an estimation of the location from which the keratometry draws its, or the keratometer draws its values. And we're taught that the radius of the circle is 3 millimeters and it's centered about the visual axis. Well, we're going to learn in a few slides that the 3 millimeters is a bit of a fiction, but let's take it as granted just yet, and understand that in this cornea, that the keratometer is reading an area that's fairly representative of the central cornea. I want to emphasize it's not exactly the central corneal curvature, and it's important to recognize that because, of course, the lens calculation formulas are based upon keratometry. And if keratometry has some idiosyncrasies, well, those are required by the lens calculation formulas too. Anyway, let's not make this too complicated. What I'm going to do is I'm going to show you a 3D map of the same cornea. And here it is, a nice wireframe map. And what I've done is I have exaggerated the imperfections in the contour of this cornea. I've made the steeper areas look steeper and the flatter areas look flatter. And you say, but wait, this thing still looks kind of cornea-like. It still looks pretty smooth. And that's kind of my whole point, that the differences in curvature in a normal cornea are really pretty subtle. I'm going to show you a cornea after keratoablative surgery that has been exaggerated no more than this one has. And we'll see a substantial difference there. Anyway, this is a patient who has undergone keratoablative surgery, has undergone LASIK or PRK, and we have our keratometry acquisition oval here, and there are a few things that we notice. One of them is that the keratometry is obtaining values out of the flattest part of the cornea, out of the part of the cornea through which the patient is actually looking, out of the visual axis. And the keratometry is going to yield values that are going to tell us that the cornea has more refractive power than it actually does, or at least than it does in the visual axis. And what this means is that when we enter the keratometry values derived in this fashion, which is to say by a keratometer, into our lens calculation formulas, we're going to say that the cornea has more power than it does, and we're going to wind up with an intraocular lens that has less power than it needs. And we're going to wind up with an eye that is underplussed. We're going to have plus spectacles afterwards to correct for it. And of course, patients who require plus spectacles are hyperopic patients. So we're going to be making our patient hyperopic. Now, we know well enough from our conventional cataract patients that they are unhappy if they obtain a refractive surprise and wind up being hyperopic after cataract surgery. But this subpopulation are people who not too long ago paid a great deal of money to achieve emetropia. And they are going to be even less satisfied being hyperopic after cataract surgery. The second thing that we want to notice is that this keratometry acquisition circle oval thing here is a lot further out in the cornea than it was in the case of the normal cornea. We'll get back to that topic in a sec. So this is the 3D wireframe cornea that's exaggerated no more than the normal cornea was in the diagram that I showed you before. And we can see that the center of this cornea is really grossly flattened. Of course, I mean, that's the whole point of the keratorefractive surgery. But the thing that kind of strikes me is that there's a lot less uniformity to the curvature in this cornea than there is in the normal cornea. And if you miss the center of the cornea here, that you're going to wind up in an area that is much more different from the center than is the case in the normal cornea. Okay. Let's get back to the idea that the acquisition circle for the keratometry that we saw in the patient who had undergone excimer ablative surgery was a lot larger than the acquisition circle in the normal cornea, meaning that the keratometry was not drawn from a circle of a radius 3 millimeters, but a circle a great deal larger. And why should that be the case? It turns out that keratometry, that the areas on the cornea from which keratometry is drawn is itself dependent upon the curvature of the cornea. Now, here we have this M.C. Escher drawing that I'm sure that we've all seen. And what I want you to see is that M.C. Escher himself is the same size in both of these spheres. Both of these spheres are the same. What I'm doing to the picture on the right is I've reduced the radius of curvature of that sphere. I've made it more curved. I've made it steeper in our sort of ophthalmic language. So the sphere, or if you can imagine it, the cornea on the right is steeper than the cornea on the left. And the cornea on the right is someone who has not undergone keratoablative surgery, and the cornea on the left is at least the central part of the cornea of someone who has undergone keratoablative surgery. It's a much flatter cornea. Now, if the Myers from the keratometer, the projection of the Myers, are, let's say, the size of M.C. Escher's head, then you can see in the steeper cornea, where the head is smaller, the radius that describes the circle about which keratometry is obtained is a lot smaller than in the flatter cornea. So in the flatter cornea, keratometry not only is going to miss the central cornea, what the patient actually looks through, but is going to be obtained even further out, further in the periphery of the cornea than is the case for keratometry for the normal cornea, sort of further compounding things for us. Anyway, this is our ablated cornea. And you can see the one thing that we cannot trust is keratometry. So we've kind of ruled that out. The one thing that you don't want to do is just to do keratometry measurements and trust those and go ahead with cataract surgery, or you will make the patient badly hyperopic. Okay, so you say, that's fine. I'm not going to make my patient hyperopic. What I'm going to do is I'm going to use the central topography values on my computerized topographic map, and I'm going to plug them in, and that is going to be what I'm going to substitute for my keratometry values. I don't have to worry that I'm missing anything centrally then. Well, it turns out that for most computerized topographers, that's not really an option. I, by the way, give an entire lecture on keratometry based on nothing but food. This time, all that I'm going to show is this annular treat. But what I'm interested in is not the chewy, bready goodness of this bagel, but of its hole in the middle. Because the computerized topographer also has a hole in the middle. So this is the computerized topographer that I use, but in essence, all Placido disc-based keratometers are the same. And what you notice in the center of the video keratographer here is a camera. And this is the video camera that acquires the image from which the topographic map is plotted. But the projection of that camera onto the patient's cornea is an area that is itself not mapped. So that in essence, with our Placido disc-based topography units, there is a blind spot right in the middle of the cornea, an area right in the center of the visual axis from which we're not gaining data. And of course, this is the most important part of the cornea, and is also the part that we just said that we wanted to substitute for keratometry. Well, guess what? This is the one place from which we don't have values. And you say, okay, well, what I'm going to do is I'm going to spend a great deal of money, and I'm going to get one of these new fancy topography units that is going to give me true central values, and I'm going to know exactly what's going on in the center of the cornea, and I am going to get a nice central map, and I'm going to take this central value, and I'm going to substitute that for K's, and that's it, and we're done with this lecture, and thank you very much. And then you actually try this, and lo and behold, the patient winds up postoperatively being hyperopic. So what went wrong here? Well, you know, the problem is something that's really intrinsic to the keratometer and to the computerized topography units too. And it's this. This is a chart that gives us the equivalence in radius of curvature to dioptric power for keratometries. And we see this dial when we look at the dials on our keratometer, that the dial will have both sets of numbers on it, the radius of curvature and the keratometry. And I'm going to ask you, have you ever wondered where this equivalence comes from? And you say, well, no, I have not. And I continue not to wonder because I know that all that I'm doing is I'm calculating power based on index of refraction and radius of curvature, and this is not a difficult thing to do, and stop wasting my time. But it turns out that that's not exactly what's going on here. So we know that if we were to excise the cornea and hold it up in air, that it would in fact be a minus lens. And it's a minus lens because the posterior curvature of the cornea is steeper than the anterior curvature of the cornea. Or in other words, the cornea is thinner centrally and thicker as we move out. Now, the index of refraction that gives us this equivalence between radius of curvature and dioptric power is 1.337. It's sort of close to aqueous, which is 1.33. But it turns out that physiologically there isn't anything that has an index of refraction of 1.337 in the eye. What it is a little bit more complicated than that. The index of refraction for the stroma is in fact about 1.375. We don't use the number 1.375 to calculate the dioptric power of the cornea. And the reason that we don't is obvious if you think about it. If we were to take the radius of curvature and calculate with an n of 1.375, what we would be getting is the anterior power of the cornea. But the posterior power would actually be negative. And if we want to combine the two, to kind of come with one combined value that represents the dioptric power of the whole cornea, what we can do is we can fudge the index of refraction down. We can take the 1.375 and factor in the curvature of the posterior cornea and say, well, you know, the index I'm going to use for the whole cornea is going to be 1.337. All that I have to do is measure the anterior curvature and apply that index, and I'll get the overall power for the cornea. And that works, but it works because it's predicated on a relationship that is fixed between the anterior curvature and the posterior curvature of the cornea. And that kind of makes sense too. You know, in a cornea that is flat or a cornea that is steep, as long as it's not pathologically steep, as in keratoconus, there's no reason to believe that either of those cases would necessarily have a thicker or a thinner overall cornea. And in fact, the curvature of the back of each of those corneas is going to be in a relationship that's fairly fixed with the curvature of the front of both of those corneas. And so we can safely use the 1.337, and this is the N that gives us that equivalence table. This is the N that gives us the value on the dials on the keratometer, and indeed the N that gives us the refractive values on our topographic refractive maps of patients' corneas. Okay. The problem's this. If we take one of these corneas and we do a LASIK treatment or some sort of a keratoablative treatment, let's say to the bottom cornea, and we've now reshaped a portion of that anterior surface, the relationship between the anterior and posterior curvatures of this cornea, that relationship that was fixed has been violated, and it's no longer fixed. In fact, the posterior cornea is now much more steeply curved than the anterior cornea is. The cornea, if you were to excise a button from the center of the cornea, hold it up in air, it would be a much stronger minus lens. And what this means is that the fudged N should be something a lot lower than 1.337. And the degree to which it should be lower is a function of how much has been ablated from the cornea. Another way to look at it is this. If the overall average N for the cornea is going to be 1.337, and we've removed tissue that itself had an index of 1.375, because all that we took out was stroma here, and that's the index for stroma. So we've taken out a portion that had a higher index, then the average index for the rest of the cornea must be lower. Anyway, I think I've pretty much beaten this horse. So what does this mean to us in practical terms? Well, you know, let's look at the error that's induced by using that fudged index of 1.337. And I know I wrote down here power equals, but in fact what I'm talking about is the error in the power calculations. So the error in the power calculations is a function of the ablated cornea over the index of refraction for the overall cornea, what I'm calling the fudged index. And what we're interested in is not really the relationship between the two indices, but the refractive power is a function of the difference between the index of the cornea and air. So I'm going to take the ablated N and subtract 1.0 from it, 1.0 being the index of refraction of air. So the ratio that's going to give us this error is going to be the ablated N, what the native stroma is, that N minus 1, over the fudged N minus 1. And that number is going to be given by 1.375 minus 1 over 1.337 minus 1. And if we do this, the value that we get is 1.11. What does this 1.11 mean? 1.11 means that the power that we're going to get is going to be 1.11 times what the real power of the cornea is. Meaning that we're going to overestimate the power of the cornea by 11%. Now, I just want to qualify this statement. I know that this proof has got a lot of parts to it. It's not that we're going to have an error where we measure the power of a cornea after excimer surgery, and we're going to overestimate the power by 11%. It's that we're going to overestimate the effect on the topography that was achieved by the ablation by 11%. So in a sense, it's an even bigger mess, because not only are we going to induce an error, but we don't know how much of an error is being induced unless we also concomitantly know how large the refractive treatment was. So even if we have a map that we can see right to the exact center of the patient's cornea, that map is also not going to represent things properly for us.